about stocks and all, but it went a bit more into math side, so I can see most of you are sleeping and all. So I won't give this into fully into maths, but I'll try to give an example and go through like how stocks work. Okay. Uh, so the first thing is, what is the full form of Starks? So it's basically scalable, transparent argument of knowledge. So as you already know about Snarks, so as there are a lot of things that Snarks have issues with, like the trusted setup, you can say, or the amount of competition that you can do inside Snarks, and also they use elliptic curves. So because of that, they are not post-quantum resistant, right? So we try to fix all these things with Starks. Yep. And why to use stocks? Okay, so you might be knowing ZK stocks and all, but right now we are just talking about stocks. So stocks are just used to prove the computation. So we want to do some computation and we want to get a proof that we did this computation. So that's why stocks are used for. ZK stocks are basically a ZK wrapper on top of stocks, which basically makes some of the elements private. So some of the inputs and all these things are made private in that. So before moving into the example of how we can use stocks, let's explore a bit about the use cases of stocks. So the first one we all know, like if anybody is in Web3, so you must have heard about ZK EVMs and all these ZK rollups, right? So what they do is they basically wrap all your transactions and they bunch it and they try to prove it. So think of like Alice is your sequencer, think of it like Polygon ZK EVM, and what it does is it basically takes all your transactions, make a proof out of it that all of these transactions are valid, and then post it to Bob. So Bob is kind of an Ethereum, the settlement layer over here. In biosciences also do the same thing. Think of we have two genetic data and we want to check if both of these data have some link or something, okay? So instead of both of the parties doing the computation, Alice can make a ZK proof of the computation that he checks that both the genetic files are linked or not. And then he can pass on the proof to Bob, and Bob can only check that proof. He don't need to go through the whole genetic file again. And the last one is AI agents. So as of now, like we have been building a lot of AI agents, and how stocks are useful is we can prove that the output generated by the AI agent is correct. What I mean by correct is that the output was actually inferenced by that particular AI agent or not. So we can give identity to AI agents through signatures and all these things. Right. So moving a bit forward, this is the example that we're gonna solve today. So I won't dive deep into the maths. If you want to understand the maths, you can do it later. But now I'll just run through an example of how it works. Okay. So this is the problem that we're taking today, and we want to prove that the 1023rd element of the Fibonacci sequence is this number. Okay. And we want a party to compute this, and the verifier just needs to verify a cryptographic signature, and he'll be able to verify that the actually prover has proved all this thing. So the first thing is trace. So basically trace is the computation. So if you check for our particular computation of finding the Fibonacci sequence, it's 1, 1, 2, 3, 5, and it goes on. So it's basically the whole Fibonacci sequence till the element we need to calculate. So this is called as the trace, and it is all the elements that is required during the computation. The second thing is a commitment. So once I have the trace ready with me, I don't want to share the raw data with the verifier. So what I do is I just make a cryptographic commitment to it. And what I mean by commitment is the verifier can later check this commitment and can check if I'm still using the same data or not. So that I'm not playing with the data anymore on the further steps, because we will use the trace in the next steps as well. So that's why this part is called commitment, because we are committing our data to the verifier by making some cryptographic hashes and signatures to it. If you guys have heard of Merkle trees, so we take the trace elements like this 1, 1, 2, 3, 5, and we make a Merkle tree out of it, and the root is the commitment to it. So that's what we share with the verifier. Now there are some rules of our game, right? So the first element should be 1, the 1023rd element should be this number, and it should follow this particular formula of a of n is equal to a of n minus 1 plus a of n minus 2. This is a Fibonacci sequence, right? So all these three rules need to be followed throughout the whole game. Whatever numbers we have generated throughout the trace, this should be satisfied in that. So coming to the polynomial side of things, we don't want to go into how all these things work, but how it happens is we convert each of the constraints or the rules into one of the polynomials. So we have now 3 polynomials, and we don't want to commit to again 3 polynomials because it will increase the bandwidth of the to and fro between the prover and verifier. So we just make one polynomial, which is known as composition polynomial, which is basically a rule checking polynomial, and we again commit to this and send it to the verifier. So Elias calculated the trace, he made a commitment, then he calculated all the rules out here, then he made some polynomials out of the rules, and then he committed that as well to Bob. So now Bob is the verifier. So Bob now has that root for the trace and root for the composition polynomial. Now there's this stuff called FRI, and you can just read it, but you won't get anything out of it if you're not into the cryptography stuff, right? So technically speaking, it just checks that if one polynomial is close to another polynomial of a low degree or not, right? So if you want to check more about this, you can just search about fast rate Solomon code in Google. But to make it simpler, you can have an analogy like this. So think of, we have two curves, okay? And we want to see if one curve, if we apply repeatedly some smoothing filter, we want to check if this curve is combined to this. So that's what FRI is. So there is a polynomial, we are adding some noise to it continuously and breaking it down into small parts, and we're trying to check if it is similar to one more curve or not, right? So we have two polynomials and we try to check if both are similar or not. That's what FRI is. And FRI is a continuous process. It goes on time by time. Like, so if we started with 1024, then we break it to 512, then we break it to 256, and it goes on like that till we get 1. And similar to the previous process, all the FRI iterations need to be committed to the verifier, right? So now I'll just get a recap of whole thing that we have done. So first we got the trace, which is the Fibonacci sequence till the element we want to calculate. Then we committed it to Bob by making a Merkle tree. Similarly, then we calculated the rules of the game, which are those 3 rules that the first element should be 1, the 1023rd element should be the number x, and it should follow the formula of Fibonacci sequence. And we again made a composition polynomial and committed it to Bob, the verifier. And the third thing is FRI iterations. We took the composition polynomial and we tried to make it simpler by applying a FRI operator to it. And then again, in every iteration, we committed it to the Bob, the verifier. And this is the last step of the whole Stark series, where basically prover has already sent all the commitments to verifier, and the verifier will ask prover to just decommit few elements. What I mean by decommit is, so in the trace of 1023rd element, I can ask him that I want to check the element at index number 6. So he need to send me the element of index number 6 along with the Merkle proof. So as Bob already has a Merkle root, he can check if that Merkle proof is valid or not. And similarly, it happens for the trace, the composition polynomial, and the whole FRI iterations. So it goes like true for. So I've given like 2 rounds here, but it happens multiple times, right? So this was the whole thing. So if you want to check, you can just take the slides from me and you can just recap of how the whole Starks work, starting from the trace, then the rules, then the composition polynomials, how commitment works, and at last how the verification works. There are some things that I've missed out here because I wanted to make it very, very simple. I guess in Snarks we have already covered this, but all of the things that I've done over here is that are done in modular arithmetic. So everything happens in some mod prime field. We have a field element and we take the mod of it and we try to solve using that. And also there is polynomial interpolation, low degree extension. You can just check about this. I just made it simpler through all this analogies and stuff, but in practical life, if you want to do this, there's a lot of mathematics involved. So if you want to check it, you can just search about all of these things. Yep, so that's about my talk. If you have any questions, pop in. Yeah, so in ZK EVM, what happens is we have the previous state of the blockchain, and we apply a set of transactions to it, the new transactions, and then we get the new state, right? So what we do is using ZK Stark. So as we have this sequence of over here, so the trace, instead of having just numerical data, the trace will have each transactions. So we'll apply transaction 1 by 1, and we check if the new state is the actual state or not. And that's how we generate a proof out of it.
Are Starks more expensive on computation than Snarks?
Depends on the computation that you want to do. If you want to basically encode an LLM circuit or a machine learning circuit in Starks, it's much more cheaper to do than considering Snarks. Basically, uh, if the computation is growing over time, then it's better to use Starks than Snarks because this have like quasi-linear proving time rather than wherever in Snarks it goes like very in kind of a quadratic form. So we don't want to use that. This is more simpler for like if you want to do a batch of transaction checking, a batch of signature checking, all these things. So Starks are the way to go. Yeah, so the size of the proof is a downside, and also you cannot directly verify this thing on chain. So we wrap this around a snark circuit, which is called as Groth circuit. Like all the ZK VMs do it, and then verify it on chain mostly. So the downside is the proof size and everything, but the pro is like we don't need a trusted setup. The proving time is like quasi-linear, and the verification time is also less. Yeah.
Is it all, this seems to be a very simple example of how like it'll not use a Fibonacci sequence in
Yes. So if you want to check some real life implementations, you need to check ZK VMs, so zero knowledge virtual machines. So you can write random Rust code out there, and they will try to prove that that actual computation happened. And how they do it is how we have a sequence over here. They have a sequence of operations and opcodes and all those things. They try to make a table, and then they try to do the same thing what we have done with the same data. Yes.
Yeah, so Arman, you were saying like the proofs go back and forth between the prover and the verifier. Does it mean then it's like interactive?
Yep. So both Snark and Stark are primarily interactive, but what we do is we apply something called a Fiat semi-transformation on both of this to make it non-interactive. Fiat Shami transformation. FIAT Shami transformation. Yeah, same one.
All right then. Let's give a hand for Arman.